tomorrow will be better. In this video, guys, I'm going to take you a little bit again to physics, most precisely in the world of mechanics. I'll be teaching you how to apply the law of moments to forces acting on an object. Let's get started. This is a picture illustration of two construction workers transporting a load using a bar. Now the question wants us to find which of these two workers feels the weight more than the other, okay? So let's get started. Solution. I know that so many of you at first sight will say, of course, it's B. But let us prove or let us show the science behind the fact that B carries the greater load. Now, I want you to know that the sensation of feeling a load comes as a result of the reaction force which an object applies on us when we first apply a force on that object. Because in accordance with Newton's third law, if I apply a push on this wall with a certain force, F Newton, this wall also applies an equal push on me with the same F Newton, okay? So it means that this person here applying a force on this floor is also receiving an equal force from the floor, which we will denote here as RB for this case, and then that of this person will be RA. So the summary of this question is, if we are able to show that RB is greater than RA, then we can conclude that worker B carries or feels the greater load than worker A, alright? So let us get started. Now, to solve this problem, we're going to use the principle of moments, which has two implications. The first implication of the principle of moments is that if an object like this one is in equilibrium, then sum of all downward forces must equal sum of all upward forces. Let me just denote it with an arrow. Upward forces, as so, okay? So let's identify all the forces in our diagram. So we have upward forces, only RA and RB. So this implies RA plus RB has to equal. Now, the only downward force in this question is 10 kilonewton. Now, to avoid mistakes, I'm going to write the direct meaning of the prefix K, which is 1000, okay? So I'm going to write down here 10,000, all right? I can call this equation 1. Now the second implication of the law of moments is the fact that if you take the moments of this object about any point, the sum of all the anti-clockwise moment about that point has to be equal to the sum of the clockwise moment about the same point. Alright, so how do we put it here? The sum of all anti-clockwise moment about, let's take moment about point A. Moment about A has to be equal to the sum of the clockwise moment about that same A, okay? But let me just remind you guys that the moment of a force is given by the magnitude of that force times the perpendicular distance from the pivot or from the point of action of the moment, okay? So with this in mind, let's calculate. We are taking this as our pivot, all right? So about point A, let us identify all the forces that will bring about or are susceptible to bring about an anti-clockwise rotation, okay? The only anti-clockwise rotation here can only be caused by RB. RB is the only force that wants our bar to go in the anti-clockwise direction. So the magnitude here is going to be the magnitude of the force RB times the distance of RB from the point of action, the perpendicular distance, which is altogether 3 meters. So this is the sum of the anti-clockwise moments. This should equal the sum of the clockwise moments. Now, about the same point, which force here is likely to cause a clockwise rotation of this bar? The only force is the 10 kilonewton, okay? So we're going to have that the magnitude of the force, which is 10 kilonewton, 10,000 newton, times the perpendicular distance from the pivot, which in this case is 2 meters, okay? So already from this second equation, we can pull out RB, okay? So let me first simplify. This means that we have 3 RB is going to be equal to 20,000, not 20,000 US dollars, okay? So you divide both sides by 3 in order to obtain RB. As so this implies that RB, the reaction on the floor of worker B, is going to be equal to, you can leave it as a fraction if you don't want decimal values. And don't forget the units, Newton, because it's a force. Now with this value of RB, we just substitute it in equation 1 and find RA. I always like to write it down because, like I always say, it's difficult to say one thing and write the other. So put RB in equation 1 implies that we will have RA plus the value of RB, which is 20,000 on 3, and this should give us 10,000. As so, all right, we are almost done. All we have to do now is to make RA the subject by sending all of this term to the right. And guys, be watchful with the sign. When this moves to the right side, it becomes negative, okay? So we have that RA is going to be equal to 10,000 and then minus 20,000 all over 3. At this point, I'm going to leave it all to you. You can decide whichever method of solving this fraction is convenient for you. But for me, I'll just use a trick here to obtain the LCM, all right? So I'll just say 3 times 10,000. 3 times 10,000, which is 30,000, minus 20,000, all divided by 3. And the answer will be nothing else but RA is equal to, if I do this, what is 30,000 minus 20,000? This gives me a 10,000 all over 3 Newton. So clearly we can see that the normal or the reaction force on worker B is way greater than the reaction force on worker A. In fact, critically looking at it, this is twice this. Therefore, we have confirmed and we can say with certainty that worker B feels the greater load. Unfortunately, why? Because tomorrow will be better. Thank you.